Welcome to today's Sendo Reliability webinar on regression analysis. And I'm not going to talk about um, maximum likelihood estimators or rank regression or things like that. That's just one or actually two different algorithms for creating a fit. And there are others, many others actually, but there's also a whole lot of models. Yet what I find in my experience and working with other people is is understanding all of the assumptions we're making and where and how we can check them and how we can recognize when something's not quite right. And so that's really what I'm meaning by the fundamentals of regression analysis is kind of peeling back a layer of, yeah, we can do an XY plot and put a line through it. And yet, is that appropriate? Is that the right thing to do? Is that meaningful for our circumstance? So that's a lot of what I want to talk about today. And all of us, I think, without hesitation or reservation, is we all have data of one sort or another. And we know how many units we ship. We know how many units we made. Sometimes we know how many come back. And we have prototypes and we get information off of those. We make measurements and monitoring systems, all kinds of levels. Sometimes, and I've heard this for the last 30 years, is we have too much data. And one of my favorite things that I point to all the time is this production line got sold a whole bunch of vibration and current sensors and a whole bunch of stuff. And it was all shiny new box syndrome, I think. And they bought the whole lot and they put sensors everywhere. Every motor had one or two sensors on it. There was all kinds of stuff going on in the plant. And I said, so what do you do with this? And they all kind of looked at me like, we don't know. They got installed. Sometimes they're in the way. But we don't know what happens to it. So I go talk to the engineering teams and they said, no, we don't have access to the data. And I go talk to the people at the director levels says, yeah, we put all that stuff in. So it's supposed to really help us with reliability of our systems and our maintenance program. And I said, well, doesn't somebody actually have to analyze that data? And they just kind of stared at me blankly. It says, well, I thought the data would be enough. And I thought, okay, I think we need to have a little chat. Having data is great, but actually doing something with it and understanding it. And one of the many tools we have available is regression analysis, and we'll dive obviously more into that. And it's really is an analysis, is what is it? Usually it starts with what do we want to learn from this, or what are we trying to find, or it might be just exploratory. What does this data set actually mean to us? And what could it reveal about patterns or things that are going on within our system? And sometimes we're looking for a change, or we're looking for a deviation, for an offset, or for a confirmation that our fix that we did for some problem actually is working. So the analysis should have some purpose up front. It's not just do it and put it in a binder and say you're done. It's about it, not much better than just admiring your data. And I think I'm getting ahead of myself in every slide so far, is I worked with one client that was making a pretty complicated medical device. And it was a radiation therapy of sorts. And they were really worried about some pumps and some cooling liquid that had to be used on the system. And there was a pump on there. And they were worried about it. If it failed during a procedure, it would really cause a lot of damage to the system. And said, why don't you put some monitoring on it, put some sensors on it that allow you to detect if it's about to fail, if the type of mechanisms you're worried about are ones that we can find, or find precursors to it before it actually fails. That might be a useful way to say, oh, we need to do maintenance on this before we start the next procedure. And the amount of discussion that went into whether we add this sensor there or not was on perception by the customers. How would we know it's doing it? How much study would it take to figure out what's the right time to signal it needs to be replaced? I got the impression they were really overthinking it, but that's what they did. They finally figured out, a way to set up this system so that it would monitor these key elements of their overall system and give them ample warning, not an emergency, not anything else, but it's kind of like, oh, your toothbrush battery needs charging within the next, couple of days. And there was plenty of time without affecting the process that you were dealing with. So that the analysis was set up to answer specific questions and optimizations at some point. So regression analysis can help in so many of these circumstances that I wanted to dive into it a little bit deeper. All right, quick show of hands. How many of you have heard of or actually check the residuals when you do a regression analysis? And if I won't ask the opposite question, do you even know what residuals are? Oh, this might be a really good discussion today because back in the old days, before a lot of computer ability and stuff, we would manually plot data on, say, a Weibull plotting paper, and we would measure the residuals, the difference between the best fit line, which was done by eye. We just kind of put a ruler around there and said this about represents where the straight line would be. And the difference, the distance from that fitted line to the individual data points is a residual. It's the miss. Think of it that way. It's our model is a straight line, yet the data isn't in a perfectly straight line. If it is, that's probably a problem with the data collection. But the residuals give us an indication of some variability in our system, and small amounts of differences are fine. Great big random differences are not so good. Yet it's one of the major tools for us to check, is our regression analysis actually a reasonable model for the data set we have? Plus, it has lots of other things, which we'll get into. All right. Now, there's all kinds of ways to do regression analysis. Let me see if I can get my pen working today. The bifoot, let me go back here. This is going to be an issue with until I get used to how to use this pen again. Simple regression, linear regression, is we've all done it. We have an X and Y axis. Let me get my pen. I actually have to have a pen. Come on. And I want red. Okay. Hopefully it works. No. Why am I not getting a pen? Well, let's try this one instead. There we go. All right. So we have an XY plot. And we may have a little bit of, I was afraid of that. I have to be careful touching this thing. And we have some kind of data set. This isn't going to work. Let me collect this pen again. And I was practicing yesterday and I thought I had it going. Let's say we got a handful of points here. And you can visualize a line through that. That won't go perfectly through those. And we have the x-axis, which in our line of work might be time, and the y-axis might be, say, a wear pattern of some sort. And we could say the longer in time, the more wear that occurs. And there might be some simple relationship between the two of those. Now, sometimes, and it's harder to do in a drawing on a two-dimensional surface, is you might have multiple regression. I might have a z-axis on here that says, oh, it depends on temperature. So we have temperature and the force of the two plates touching each other, for example. And that dictates or models the amount of wear that we have over time. And these are straightforward, clean models that allow us to find relationships. And it allows us to take one, two, three, or even way more than those types of relationships or sets of independent variables to create a model saying that if it's humid and it's high temperature and the speed is so many miles per hour, the amount of wear on the brake pads will be X. And then we'll monitor how long it takes before it creates a critical amount of wear, and then we replace those pads. And you can imagine that you could find 30 or 40 different variables for the wear on brake pads. And it's one of the basic approaches to regression analysis is you want a model that's good enough. And we'll talk about it as one of the problems later is when you pick way too many variables, and you want to pick enough that it accounts for the vast majority of the variability that you're seeing, yet you can overdo it. But the very first part here is that a simple linear model on an XY plot is probably we're all familiar with and have done it numerous times. It is a great place to start. The trouble is that it's not the only option we have available. So if we know it's temperature and humidity that do this, affect whatever we're measuring, then we may have a three-dimensional plot. Now, general linear models may include all kinds of different things. And trying to figure out where my notes went, but it can be things like analysis of variance, ANOVA, and other models that are actually regression models where I may have multiple variables as the independent variables, things that we're monitoring that occur in our system or forces that affect our system. And we have multiple outputs, things that we're interested in, not just time, but maybe time and production yield or time and stopping force. And it allows us to do pretty complex models as to figure out, well, what's important, what's the major contributor to this particular issue we're dealing with, and so on and so on. So there are ways to go from simple models to more complex models with simple linear models that are basically y equals mx plus an error, uh, uh, mx plus a constant plus an error. And the idea is that you can put it in regular scales and you can draw a straight line. And the straight line gives you a visual when you compare it to the actual data saying, yeah, that kind of is a straight line. That makes sense. Now, sometimes we do proportional models, and one of them is a Cox proportional hazard model. And one of the benefits of it, if you ever run into this circumstance, it could take into account non-variable data, such as discrete data. It might be the left side of the car versus the right side of the car for the brakes, using that example. So it might be left side, right side on the same vehicle, but they behave differently. And so we're interested in modeling what's the effect of all of these combined forces on the wear pattern of that thing, of these brakes, but we're interested in the left and right and how different they are. It may involve different groups of people. Maybe the Europeans use your product in a different way than the folks in the US. And, and that's a discrete type of variable, and proportional modeling is one of the models that allows you to account for those. And there are literally dozens more linear models out there and variations of that, and they can get very complex pretty quick. Yet they all have this underlying fundamental that it's really just standard scales, draw a straight line. And obviously that gets more difficult when you have more than one scale, or I'm sorry, more than an XY plot, and then it's three-dimensional, four-dimensional, and so on. But it can be done. Oops. I don't know why that's, oh, I'm still in the pen. Let me get out of that. Bear with me. I'll get a hold of this eventually, figure out how to do this. Let me do that. All right, another whole class of regression analysis, and you may or may not have run into this, is when you have a, a time factor that describes the variability of your whatever it is you're trying to model. And so one of the classic examples I ran into was actually a very poor example. And I was at the time I was taking a master's level class on time series analysis, and I saw this at a school board. And so this is time, pardon my small handwriting, and this was class size. I'll just class size, number of students in elementary school. And the data over the last 25 years, and I'm not drawing it as accurately as it was in the system, you can see that it has a slight rise to it, but it has a cyclic pattern. And they were asked, or the school board was talking about, do we need to build another grade school? It's a reasonable thing, and the existing grade schools were a bit crowded, but not terribly overcrowded. But it also, as you can imagine, takes years to build a new school. And so the person that was in charge of doing this analysis said, well, given the pattern and the analysis of this, I expect over the next 5 years that the children going to our grade schools will look like this. It will more than triple. And when asked about it, he said, well, I only know how to do basic analysis, so I only took this point and this point and drew a line off of it. And so one of the board members, being an astute, intelligent person, said, well, what if we would have done this 6 months ago? You would have had a projection saying that we would end up in 5 years with no students. And at that point, somebody said, why don't you just draw a line right through the middle of this gentle rise? Oops. I guess I really do need to figure out how to use this pen. All right. Well, I'm not going to try drawing it. So if you draw a line through that wiggly part for the last 20, 30 years and draw that gentle rise as it's moving up, you would have a reasonable estimate over the next 5 years. And then if you got fancy, you could do a lay over the second part of the model that accounts for that cyclic pattern. And it was like every 5 years, it would be another generation of families would be in the area and their kids would go to the school and then they'd move on to grade school. Yeah, the hockey stick curve. They were, I don't know if he was just naive about regression analysis or really wanted them to build a new school or what. I don't know. But time series modeling, like a simple linear model, can be very simple. You just do an average of all your data set and just draw a line through the middle of your variation. Now, many businesses have cyclic patterns in their shipments, and they may have for example, if you're in the consumer markets and it's an item that is often used as a gift in the holidays, you probably have a seasonal variation. If it's for back to school type product, then it follows the school's year. And knowing that it's cyclic like that, you can account for that. You can use a time series model to account for that seasonal variation in a whole range of different ways. And the ARIMA model accounts for, say, that gentle rise that's going on, and you can add the cyclic part of it, and you can do a variety of other activities to account for the variation you're seeing in that, including, let's say it's not a straight line pattern moving forward, but it's increasing or decreasing. ARIMA models and variations of those can account for very complicated, say there's two seasons going on. There's both the, say, a 5-year cycle and a 1-year cycle, and you can account for that. And I'm thinking back to electrical engineering and sine waves and all that good stuff and how they can add and subtract from each other and create all kinds of exotic models. But the idea is that time series models account for that seasonality type stuff that we often run into. Yet in my work with so many different reliability engineers, I rarely have ever seen somebody using time series. Now, warranty typically follows the seasonality of our sales. And understanding that and working with the folks in finance to understand that it's not a straight line, it's a seasonal thing. And hopefully they understand that. But way too often I don't see that. So one of the major types of regression analysis is time series models. And hopefully you can dive deeper into those. And some of it's pretty basic, but it's usually not in our systems that are used for uh, life data. So we don't see it like Weibull analysis is usually not a seasonal type thing. It certainly can be if we account for, say, temperature that affects our product. If it's lower temperatures, it may not wear as quickly versus higher temperatures. Modeling it to account for that could use one of these more sophisticated models. Now, nonlinear models, those we do use, things like exponential and power law, and as ways to model the relationship of the time to failure distributions. And so like voltage often is a stressor on electronics, and power law model is a great way to explain that. It's just whatever our x value is, and it has an exponent of some sort. And exponential is e raised to some variable that we're interested in, and so on. Now, polynomial is that simple extension to the simple linear model, where we know we have a curve. Our data is showing a distinct curve. It could be curving up or down, but the idea is you could fit a straight line to that, and it would be okay for the average over the data set. Yet, I'm going to hesitate here to draw the. You can imagine is I have a an item that's rising at the start and it bends over and it starts coming back down. Now I can fit a line to that. It will say, here's the best fit line for that data set. Yet at the beginning and end, the data is below the line, and in the middle, the data is above the line. So it's not an accurate representation of the data set I'm using. So doing a polynomial model allows us to model a curve. And so that's what they mean by nonlinear. Now, there's also a whole class of nonlinear models called nonparametric nonlinear models. And the example of that is machine learning algorithms. And it's a way to use lots and lots of input variables and lots of output variables and find a pattern, usually by training, that allows you then to get a reasonable representation of sometimes very complex systems. And I first used one of these models, was it back in late 80s, early 90s. And it was for a extruder that had 8 heating zones. And they were obviously not independent from each other, because if you heat up one, it would have residual heat would go into its neighboring areas of this extrusion line. And So we knew we needed something that was nonlinear to model how do we set the parameters on our heating elements such that we got the outputs that we wanted. And they were variable or many uh, aspects that we were looking for as the output. Uh, it worked beautifully. It was a devil to try to explain to anybody how it worked. And so we ended up abandoning that approach because we couldn't explain it to our managers what it was actually doing. And they didn't really like the idea that it wasn't an XY plot in a very simple thing. And trying to explain to them that if you don't have independence between the variables, then the simple linear models and its variations really don't work. The linear models just don't work at all. And some of the parametric linear, nonlinear models also don't work, and they violate all kinds of problems with it. And yeah, we'll get close enough, but it's pretty bad in general. So we explored these machine learning type algorithms way back when, and it was actually pretty accurate for us to, as engineers, to figure out how to set up our extrusion system. Yet it was really difficult to explain to somebody else. Now, this is three different various classes of models. Now, there's a whole bunch of other ones out there. And there's things called like cluster analysis and cloud measurements and uh, dealing with stratified data. And there's different models that deal with that. There's models that are just fascinating of how they work. And I don't, I rarely, if ever, get a chance to use those kinds of models. Most of the data sets we have, a simple linear model is the place to start. And then you assess that model. If that's adequate, you move on. If it's not adequate, you find a better model. Or maybe the data set itself, say it has some discrete sets of elements in it, like left, right, or uh, from vendor A or vendor B. Well, then I have to typically would go to a Cox proportional hazards model to look at something like that. So the idea is you select the model that fits your data set. Now, cluster analysis and these other really cool ones, they do use a lot of computing power, which we have, yet they can really lead you astray if less you really understand how they work and what they're telling you. So buyer beware with the more sophisticated ones, just because they're more sophisticated. Make sure you know what you're doing with it. All right. Now, some of the problems with regression analysis. I hope you already know some of these or all of them. Yet I've seen it in the news. I've seen it online. I've seen it with folks I work with in different situations. They draw a quick model and do a quick regression analysis and say, oh, that must be the cause. If we turn the heat up, that must be why it does what it does. And I'm like, you need to dig a little deeper here. And because the regression analysis is just an algorithm. It just says, oh, there's a data point here, here, and here. And if I wiggle this straight line through here to find the smallest deviation from the line from all the points there, which is what rank regression does, and maximum likelihood does it in a slightly different way, is that's a good model for those data set we have. That's all it does. It doesn't say what's the physics or chemistry here, what's the phenomena, or how does this or cause that. And that's why, these medical trials often have extensive sample sizes and blind testing and all kinds of safeguards to really peel back, is there a causation here or not? And can you detect it? But it's also coupled with a lot of science saying, well, here's the chemical reactions, here's the biological responses, here's, whatever it is. And then we should be able to measure it. Now, when I'm heating something up, we can go look at things like diffusion rates within the bulk materials we have. We can look at dissipation and how much heat is going to radiate off, how much heat is going to conduct off, and so on. we can go into thermal modeling tools to get a pretty good idea of how temperature is affecting this area of our system. And then we can verify that with some experimentation and say, oh, here's the relationship. Here's a model that describes that scientifically confirmed causation. Now, sometimes we do that just by gut feel. Be very careful if you've run into a model that describes some system but has no fundamental physics or chemistry or scientific based understanding of why that relationship exists. Now, many of you have probably heard of there's a relationship that somebody came up with years and years ago saying whatever Major League Baseball division or group wins the World Series, then the stock market will either go up or go down. And it was a simple regression. It's the AL, the American League or the National League. I think that's the two of them. You can tell I'm not a baseball fan or pay attention to it too much. And I don't remember which one was which, but if one of them wins, the market goes up in the next week and vice versa. Now, can anybody explain how that actually works? What's the connection there? Is one league more vested in the market or they have more stockholders behind them, or I have no idea. And I don't think anybody does, but it's a classic, really solid, very good fit, well-fitted model that says one team wins versus the other, the market's going to go up or down. Now, I haven't checked in the last few years if that's still true, but if you look at enough pairs of data sets, you will find relationships, but it's not the causations. And one story I heard years ago is this young woman or young girl as a school project had a helium balloon with a note card on it saying, "Hi, I'm Mary. I'm, 10 years old, and here's my address. If you find this, send it back to me." And let the balloon go. It went out of sight. And about a week later, yeah, coincidence, Bill, exactly, coincidence. And so about a week later, a young girl named Mary found the balloon, and they had the same last name. They both liked ponies, and there was like 15 things this reporter came up with. But what they didn't say is they asked both Marys like 50 questions, and they found 5 or 10 things that these two girls had in common. Their favorite color, their favorite song, and a handful of other things. Total coincidence. If you interrogate your data set and collect data on every variable you can think of, you will find pairs that seem to relate to each other in some way. They have some nice straight line relationship between the two of them. That's just coincidence. If we look hard enough, we could probably find a data set in your world that relates to who wins the World Series or if the stock market goes up or down. But it's a small world, and if you look hard enough, let's say 100 different variables, you will find things that are showing a relationship of some sort that you can model. So the caution here is don't go looking for straight lines. Go looking for patterns. Now that may be exploratory, and it may lead to a discovery of a relationship that actually has some tangible causal relationship between the two of them. And that may be very important. But all too often is we just plot the data a dozen different ways and go, oh, that explains it. And then we're off and running. And then the next week, it's just because our data set was limited, it doesn't project well into the future. We can make really poor decisions unless we understand what the regression is really telling us. Sometimes we have a missing variable. I do need the pen for this one to explain it. So let me try this again. Let me get my pen on. There we go. Get my cursor down here. And so we have an XY plot. Oops. Ran out of deal. And let's say this is wealth, net wealth or net earnings of somebody, and spending. And I heard about this one a few years ago. And they said, all right, if you don't have a lot of wealth, you don't spend a lot of money. It was kind of the idea that they wanted to do. And they expected to see a relatively relationship that would be a straight line. If you have more money, you spend more. Well, that doesn't turn out to be true. Is what happens is there's some people, I'm not going to draw all the data parts because eventually my screen will choke on it and ignore it. All right, let me get my pen again. And there were some wealthier people that lived pretty frugally. They didn't spend a whole lot of money, while there were other people that, as you can see where I'm going with this, um, I think the speed at which I touch the pen to the deal and or I'm hitting a separate button on this pen. Um, there's some people that spent above their means. So how would you model this? You know, if you don't have a lot of money, it's not possible to spend a lot of money, although some people try. I've run into a few of those. But sometimes the data sets are reflecting not just on how much money you have, but on your attitudes towards spending. What is just your lifestyle, how much you're going to do. And good question there, Bill, on how do you check yourself to minimize coincidences? Well, it goes back to that physics and chemistry. Is there actually a reason why this relationship exists? Is there a story behind it? Is there some phenomena or linkage or I always say science and chemistry, but it's some story behind it that says, yeah, when we do this, then this software does this and it changes the output. Or like a controller on a heating cell. When the temperature hits the trigger point, we turn off the heat, we lower the amount of current going into it. If it gets too low, we turn the heat back on, we turn the current back up. If it doesn't have some story like that, it's really hard to use it in a meaningful way other than it happens to be a coincidence. So the missing variable is when you have data sets that really tight don't really follow a straight line if that's your hypothesis, you may be missing a variable, and it may be their attitude about spending. Maybe the people with some wealth have a penchant to save more because of some objective they have, or that they are comfortable in a lifestyle that doesn't require a lot of spending, and vice versa. So the idea is that if you see data sets that really don't fit a simple model, and here, if I draw a straight line, and I hesitate to use my pen, if I draw a straight line through the center of the hypothesized idea, the way to check this is that you look at the residuals. These are these pieces here, the difference between the data set and the model. And of course, this probably be a whole cloud of data sets out here, depending on how much data on it. And what you see is that if you look at it, the residuals in this section are very small. The residuals in this section are very big. And one of the assumptions is that the residuals will be constant and normally distributed about whatever model you use. And so that's why I asked about residuals right off the bat. If I plot just the residuals, it should be a nice straight little line. But if it does this and shows a pattern where they're increasing over the duration or over the data set, or they have some other pattern that's obviously not normally distributed, randomly normally distributed, then we're missing something. There's some other element to this model that should be included to explain the data set that we have. I have no idea, Johan, where Grouse Point and St. Clair shores are, but I imagine that's different lifestyles or different size housing or something like that. But the idea that is the residuals give us a real clue if something is a good model or not. And all too often our data sets or our statistical packages don't provide these residual plots automatically. So missing a variable is one major problem with when we look at our data. Always plot the data with your curve or your fitted line, so you can see if it's reasonably represents the data set that you have. I'm starting to not like my systems today. Come on, you can restart. Let me get out of that. There we go. Sorry about all the technical problems here. I'm gonna have to rethink this use of the pen stuff. Another problem, and I'll just describe this one, is let's say I have 2 points of data. Well, let's start with a simpler one. I have one piece of data, one number, and I want to do a regression analysis to it. I can fit an infinite number of lines to it, just simple linear extrapolation that takes two variables, the slope and the intercept, to describe that line. Yet I only have one piece of data, and I can draw an infinite number of lines that equally well fit that one point. It doesn't really mean anything to draw a line through one point. I hope that's obvious. Now, if I have 2 points, I can fit a single straight line through it. It will be the best fit. It will go perfectly through both lines, and it's overfit. I have two pieces of data, and I have two variables in my equation, the slope and the intercept. And what I'm basically doing is I'm consuming all of the information that is in that data set. For example, if I have 3 points of data and they don't happen to fall on a perfectly straight line, I can fit a model, say a parabola or a curve equation of some sort, that perfectly goes through all 3 lines. Now, my model requires 3 different variables. Again, I'm overfitting that data set. Now, I can get really crazy and draw 3 data points, and I could use an equation that has 4 variables in it, and it might provide this oscillating line that happens to go through all 3 lines perfectly. Yet in between it, there's big swings of one sort or another. Now, hopefully you can visualize, since I'm going to hesitate using my pen, the idea is that it grossly overfits the set. Now, many of our regression analysis tools will say, oh, you've got a great fit. It perfectly describes your data. That's something to be very suspicious of. And so again, plot the data with your fitted line to see how well it represents it. And the basic premise here is you want just enough variables to describe the bulk of the data set, but not every single point. You don't want to overfit it. Now, if I have, say, 200 data points, and on a plot, it looks like a nice, simple line would fit it, you can get away with just 2 variables just fine, realizing that it's not going to go perfectly through every single data point, and that's okay. Now, if I have a equation that has 201 variables in it, I can go through every single point and increase the goodness of fit. Yet it violates this idea of being very frugal, since I have trouble describing that other or pronouncing that other word. You want just enough variables to describe the behavior of your data, but not another set. not another piece of another variable. You want to be very frugal in how complex of a model you use to describe your data set. It's one of the uh, complaints about machine learning algorithms is that they often then have a whole lot of variables going on in the model. And there's claims of overfitting. It's why people today can say they can spot something that's written by AI because they seem to follow particular patterns better than other ones for whatever reason. But I don't know if that's an overfitting problem or not, or a characteristic of it. So the idea is that whatever model, whether it's linear or nonlinear or whatever, is always start with the simplest models, simplest equations, and then work your way up into where it actually describes the data set well enough for you to make decisions with it. And that relationship has some foundation, whether in physics or chemistry or something like that. All right, I got three more here. I want to talk about extrapolation. The, one of the things we do in reliability engineering is we extrapolate, right? We have a great data set like this. It might be on a Weibull plot. And I guess if I just tap it, it doesn't work. And what happens is that we have data for, say, 6 months in the field, and we want to know what's going to happen in the future. And so we push beyond the data set that we have and might go from 6 months of data out to 10 years. In basic undergrad statistics and in basic textbooks about any kind of statistics, it says never do this. Never go beyond your data set. Now, in reliability, we often have to do this. We have a year's worth of data, and our boss says, what's our warranty going to be next year? And the units that are already in the field, and we have a 2-year warranty. Well, we don't. The perfect answer is, well, let's wait a year and a half and we'll have all the data and I can tell you. Well, that doesn't usually answer our boss's question. What is it going to be? What's the prediction of this? The issue I have found with this extrapolation problem, is that you need a really good fit to start with a good understanding of what the behavior is. Now, many of you that have warranties and done any warranty analysis know that if you, let's say you have a 2-year warranty period, after the, or just before the 2-year warranty, in some industries, people say, oh, let's take all the ones that we know aren't working and get them replaced while they're still under warranty. So you get a little surge right before the end of warranty. And then after that, you don't. Or you might get another surge depending on the product, but you have to say, no, it's out of warranty, and then it's a customer relationship problem. But the idea is that near the end of the warranty period, oftentimes we see this uptick in the number. And so if we're plotting that naively, we may end up with a curve like this that's bending upwards. And we may then fit a line to it that has a curve into it. And so our prediction goes up when it really shouldn't, because there's some other phenomena at play that's causing that phenomena to occur. The other issue is if this line that's fitted on our actual data isn't accurate, it doesn't account for, say, a slight bend in the data, a slight increase or decrease in the phenomena, or we use a Weibull plot versus a log normal plot. Now, those two curves are often very similar in how they fit data, yet they are different. And so the worst case I saw was a expert witness on a case is the analyst that was working with the field data. Every single set of field data would drop it into Weibull++ and run the wizard, the fitting wizard, to say which is the best formula to fit this particular data set. And pretty often it was Weibull one week and it was exponential the next week. It was gamma the week after that. It was, it just kind of, as a machine, said, for this particular data set, this is the right distribution. And as you can imagine, each of those curves spin off in a different direction outside the length of data that you have, this data set you have. Some will rise sharply, some will fade off, some will do a nice straight line. And so their ability to predict what the next month or the next year's warranty is was really, really bad because it was just this wagging of random numbers out there of the next 2, 3 years. And it was all due to them not understanding what was dominating their failures and fitting it in general and then getting a decent fit. And they were doing mixed failure modes, all kinds of other problems with it. But the idea was is that you don't pick the algorithm's best fit unless you have a real reason to do it. Now, most things that we deal with Weibull is usually pretty decent, but there are exceptions. If it's repair time data, for example, I would almost always go to log normal because it fundamentally fits the type of data set that is being created. And Chris Jackson went into length about this in a couple of his webinars. But the idea is that extrapolation is fraught with error. And making good, decent regression analysis and confirming you got the right model, both scientifically and fundamentally with the causation elements to it, and you have the right model for the data set, allows you to make a reasonable estimate. And I highly recommend, especially with warranty, is that the example is next month, I'm going to predict we're going to have 15 more returns. Check yourself. Don't just rerun the model, but what did your previous model expect? I expected 15, we got 16. Okay, close. Next month I expect 15, and we got 17. Okay, I think it's 2 points of data, it's not really good. Let's rerun the whole set. Can it predict it? Keep checking your models. Always, always recheck it as you get more data available. It'll save you a lot of pain in the future. Remember, it's just the current estimate of what's going on or current representation of what's going on. Okay. I don't know how I brought that back so fast, but I did. Prediction certainty. There's two aspects to this. It's not just confidence intervals, which tend to broaden out as we go further, extrapolate further into the future. The other uncertainty is, did we pick the right model? So I got a little bit ahead of myself on this one. And doing exactly what this one analyst was doing is try all the models and see how much variability you get in your prediction. That's a representation of this data set could be modeled dozens of different ways, and they'll all give us different answers. Unless you have a really good understanding of which models fit this type of data, the way it was collected and so on, we really can't materially pick in a meaningful way. So understanding the data set and the model that describes it appropriately from that science, chemistry point of view allows us to reduce the uncertainty about how this prediction is going to behave. And then that stepstone of every month I get more data and I recheck the model is keep tabs on yourself. How accurate are you really? And understanding that further into the future is going to be more uncertain, but monitor it and check it. The other part is that there's measurement error. And I'm going to go back to warranty again, is that not everybody returns their iPhone when it fails for a new one. They switch over to Samsung or whatever product it is. So you may not know of all the failures in the field. That adds uncertainty to your prediction. If something changes the user's behavior that they want to switch brands, they're not going to, if they have failures, they'll take it as an opportunity to switch, which is outside of the fundamental element of does that product still work or not work for that particular customer. So there's all kinds of other variables that we don't often include in models that add fuzziness to our ability to predict into the future. Now, is this product going to meet our warranty requirements when we're still in design? Sometimes it's a shrug of the shoulder and we hope for the best, and otherwise we can do all kinds of different evaluations and testing and modeling and so on. Yet we're still never going to be certain. And so understanding where those variabilities are, what's the min-max types of stuff, what's a reasonable estimate going into the future, all should be conveyed as you make a statement about how it's going to behave in the future. It's not, oh, we're going to have 15 failures next month as a statement of fact. We don't know that until after the end of the month. And then even then, we may have some that are being shipped late. They may have failed during that month, but they only got our attention 2 months later, and so on and so on. So there's lots of uncertainty about this. The models are not perfect. And too many people I've run into have said, but here's the regression, here's the Weibull plot, that has to happen. I'm like, no, it doesn't. You're not accounting for all the variables here. All right. Last slide here. And I was going to draw a whole lot, but I'm tired of battling with this thing. I've mentioned functional form. The model that we use should relate to the actual data set. And things like overfitting or choosing the wrong model, if we use the simple linear regression when it's actually a parabolic shape to our data set, we're not using the right form of regression analysis, the right tool or approach or mathematics to create that regression. And even better is that if you understand what is the underlying relationship and can create a model that accounts for that science or chemistry type relationship. So if you have a chemical process, we all would probably pick an Arrhenius relation or an Arrhenius model to describe that behavior over time is in relationship to temperature. We do that for accelerated testing fairly often. Unfortunately, if temperature has nothing to do with the time to failure of our product, the Arrhenius equation really doesn't help us a lot. It might actually fit the data set, yet there's no underlying reason that temperature has any effect on our product. Then all of those things about prediction and estimating and describing what's really happening through that coincidence that it fit that data set is out the window. And so think hard why you're using Weibull versus log normal, or you're using Arrhenius versus a power law, or you're using some other form of analysis to describe your data sets. There really has to be a solid understanding of why you're doing what you're doing. The other one that we often assume is that each data point that we observe, say it's temperature measurements, on this extruder I worked on years ago. If I'm monitoring zone 4 and I'm watching it over time, it's not reasonable to assume that the reading I make this minute is going to be independent from the reading I make the next minute. There's a big chunk of iron there, and it has a lot of heat capacity. So that even though I'm adding heat to the system, it's going to rise in a nice, simple, slow way. And so my reading from minute to minute will be highly influenced by where it was just a moment ago. Right? Now, if I'm making measurements on a production line and I'm say it's a dimension of something or the size of a hole that's drilled, and two pieces coming off that same drill part of our process may be very, very similar. Yet if I take one today and one tomorrow, it's likely they're going to be different. And some of it is tool wear, some of it is the way the placement is. Maybe the changes are in the cutting of the blank itself, and so it has slightly different dimensions. And so where the hole is located, it changes slowly over time. One of the things that all of these regression models typically take into effect, except for the time series, which accounts for these cyclical type behaviors like tool wear, is that each observation is independent. It's as if we had all of the products sitting on the floor from our last weeks of production, and we take random samples and make the measurements. Totally random samples and make they're not next to each other in any way. And that's a simple example of that. Sometimes that lack of independence is okay, and we can live with it, but sometimes it really distorts how the model shapes up and behaves and informs us as to what the patterns are. So be very cautious that the measured elements of your data set are actually independent from each other. And it's also a case where you have a missing variable. If they're not independent, there's probably some other variable that describes their behavior as they come off the production line, for example. And I mentioned residuals earlier, is that they need to be, whatever that word is pronounced, homoscedasticity, I think, is constant over a range. So they don't fan out or change over the spread of our data set or over the time or the sequence of measurements and so on. But they're also normally distributed. If it's truly a random observations of our data set that are independent, we wouldn't expect a cyclic behavior of that or a trend within the residuals from our data set. So take a look at residuals. They should just be normally randomly distributed about our fitted line. If not, there's more work to be done to describe what's really going on. And then multicollinearity. I don't know why statisticians come up with so many of these difficult to pronounce words for me. Is when you have two variables, you have two uh, inputs into your model, say A and B. If they are perfectly correlated to each other, you don't need one of them. So if I'm measuring two zones on this extruder that are right next to each other, one goes up, the other one is likely also going to go up just because of the heat transfer. And so in our case, they were pretty well correlated to each other. So we only measured the first and I think the fifth zone that were far enough apart that we didn't see them being correlated to each other. So it's a way to not avoid overfitting is when you have too many variables that all describe the same relationship. So it's another thing to really avoid. So I hope I haven't scared you completely away from doing data analysis and regression analysis, but I wanted to raise the awareness of all of the range of styles that are available to us, and more importantly, a lot of the downsides that paying attention to residuals, to selecting the model, just understanding the phenomena that's underneath the model. Why is it that form or that shape or that behavior? All of those things go into doing regression analysis. It's not just dump the data into your favorite software and hit, fit. That's the easy part. The rest of it is where the engineering takes place. And that's where the real value of data analysis or regression analysis takes place. All right. Sorry about all the trouble with my pen. I'm going to have to find another way to do this with the software that I'm using, or find a different software package to present. But hopefully it wasn't too terribly distracting. Hope you picked up a few things of it. And I'll stay on the line here to see if there's any other questions and stuff. If you're listening to the recording, there's a comment field nearby, and there's always a way to get in touch with us. So if you have questions, please let me know. I'd be more than happy to address those.